Good morning to everybody. Today we are starting the lab number 6. In this lab, we basically deal with two particular aspects that are particularly important. The first one is basically concerned the possibility of perform algebraic operation in our image matrices, while the second aspect that is also particularly important concerns the possibility to use as a derivation of this operation, algebraic operation, what we call the spectral indexes. Okay, as you notice, I have already started the software, and so we are already on board with the software. And starting with this exercise, we are opening the file. So you see in the main menu, we are opening as optical sensors. Then we are going to Landsat, and then we are opening with GeoTIFF with metadata. And in this is the submenu sequences that we already know. Let's open the data sets. All right, let's go to the for example, I don't know where you have memorized the data. Okay, I'm going to the right folder in my laptop. All right, so, and I'm taking out Northwestern Italy, and I'm taking Landsat 8, all right, and I'm opening the metadata file, the text file. And I can, you see that the convention of the number is LC stands for Landsat 8, calibrated Landsat 8, and then the orbit identificators, and then the acquisition date. All right, you see here, that means that this image has been acquired the 14th of April in 2020. All right. Okay, that is not so old. It's more or less 1 year ago. Okay, double click on that, and we are opening the file. So you see how that's being represented. Is the visible as in the preferences? I'm zooming out. All right, you see. And you see, I'm putting that in the middle of the windows, and it seems to be not too much contrasted. So I can see, you see, optimize linear here. I can go to, for example, to Gaussian. You see, and so I have something that is more with a better brightness and a better contrast. So you see here is the port of Genoa, then here we have Torino and the Lombardy in the eastern part, and here we have the border with the France. Okay, so we are in this kind of representation, and we can obviously go to the data manager or click right click on our Sphinx. I'm sorry. I have these things here. I'm sorry. I cannot get it out. All right. Okay. I'm going to the data manager. You see, I'm sorry. I need to close this window. All right. Here it is. Okay. This is the data manager. All right. So I press on this icon here. You see, you remember the data manager. Okay, this is the data manager. All right, and I can represent that with a false color. I'm sorry, and so I am associating to the red channel the near infrared, then the red channel, and then the green bands. I'm loading in the same view the data. And you see, I have here the false composite. I'm sorry again. All right. So also here I can stretch this data in a Gaussian way, and you see here I also improved the brightness and contrast. And just clicking on the layer visibility, you see, I can have the stack of the different images. All right. So what we can say, we can basically say that these images we are we are now visualizing from an iconographic point of view are the image you see here, where we can find the city of Turin. You see here, and this is both in visible and both in false color. And so you see here that these images are nothing more than matrices, numerical matrices, that they have a size equal to the number of rows and column. And if I'm not mistaken, the resolution of this image, you see here, I'm taking the data manager, and for example, I'm taking one bands, you see, and I can click on file information, and you see that this image is more or less 8,000 by 8,000 for 7 different bands. And remember that the first number is always referring to column and the second to the lines. And we have 7 different bands, you remember. The 4 bands, the first 4 bands are the visible, and then we have other 3 in the infrared. So every single band, a single is around 8,000 by 8,000. That means that contains more than 50 million of cells. So what we are visualizing here is not then an image matrix that is around 8,000 by 8,000. And you see, in this image, in every single cell, we have a digital number. And just to remember what we said, this digital number, in order to understand, just clicking with the right-clicking in the name, you see here, I can go to the quick starts, you see here. So I'm clicking in the pop-up menu, the quick starts. So now it will take a while to redefine the quick starts, and is doing that right now. So in this moment, the procedure is evaluating the more than 50 values of data for every single 7 bands, is so processing more or less 350 million values, digital numbers, in order to build up statistics, extracting the parameters, that is the mean value, the maximum and the minimum value and standard deviation for every single bands, and is building also the frequency histogram, and therefore is calculating for every single digital number how many cells have this particular digital number. All right, here we have the windows, the statistics. You see, in the upper part we have the graph with the x-axis the wavelengths, and in the y-axis we have the number of digital number that they have these particular values. I'm sorry, how many values? Yes, are in the distribution. All right. So you see, these digital numbers are represented by 0 to 665,000, more or less. So that means that we have more than 65,000 possible combination of digital numbers. So in this first diagram, we have all these lines that are representing the standard statistical parameters that are in black the mean value, you see here. In the green, with the green lines, we have the standard deviation plus or minus from the mean value. All right, so you see here the standard deviation for every single band, and with the red lines, we have the minimum and maximum values of the distribution. You see here the minimum, here, and the maximum, and you can read that in the tabular values here. All right. So you remember that in this button, I can also represent the different histograms. That this is, for example, for the band 1, in which we have you see, the most part of the value of the digital number are distributed on a relatively low interval of values with respect to the total distribution. So that bands that is represented a piece of blue of the visible bands is fundamentally very dark because all the values are concentrated towards the origin, and especially is the bell is very narrow because it's representing a very low standard deviation. And you know that the standard deviation is the distance between the mean value. All right, so you see that the mean value is around the maximum of the distribution, so that means that the brightness of this image is very low, so that means that is dark. And being this bell very, very low, I mean the contrast is very low. So if I'm enlarging also this part, you see, I can represent other histograms, and you remember here, I have these different histogram. I can add all these histogram, band 3 and band 4, and you see, and we have all these diagrams that are all shifted towards the origins of the representation that also gives us a measure how we can display this image. And the colors that I have here in this histogram are the representation of the different histograms. You see that the peaks that we are represented are moving towards the origin as long as the wavelengths of the central band. So this is more or less the effects of the selective diffusion that you remember is selective because it affects the visible more than the longer wavelengths. And this is the clear representation of the effects that we have this selective scattering that is affecting most the lower wavelengths of the visible. In particular, you see the blue band. Because I mean the blue band is the histogram, the red histogram, and you see we have the maximum there, and so that means that we are going here. So we are not talking anymore about calibration, but we know that when we want to work from this data, as we said in the lab number 5, this calibration must obviously be done. And of course, we can also add all the other histograms, and you see here, and there are very different histograms of the infrared bands, and you see that the maximum has a very higher digital number. So you see, we have all this representation, and so we saw that the radiometric resolution of this image is that all these numbers are represented in intervals between 0 and more than 65,000, which basically means that we have having a radiometric resolution that is using 16 bits for every single sample. All right, let's close this window. And as I remembered before, these are numerical metrics. And so with our numerical matrices, we have the possibility of doing a whole series of possible operations. Then imagine, for example, that the fact that I show you, for example, here, you see, if I'm loading Excel in this case, you see, in this Excel, I just can open. I just showing you an example. For example, you see here I have some numerical values that could be the digital number of the cells. I'm writing random values in this very small sum matrix. You see, this is a matrix of 2 columns and 3 lines. In this matrix, I can build a series of typical operations. For example, you see, I can add a constant to all the digital number, for example, or I can subtract a constant to every single values, or to construct exponential between the square root of every single values, or I can do many other numerical operation. For example, I can sum a constant to every single image. So in this case, you see, I'm writing an expression where, for example, here, open the bracket, this cell plus, for example, 1,000 value, all right, I can put the results here. I can take this formula here, and I'm copying all the other cell, you see here, for the column and also for the second column. And you see here, you see from this very original matrix, in Excel, I perform a simple operation. I just add a constant to every single value, 1,000, all right? So let's close that. I don't want to say that because I mean it's very trivial. So we are in the same condition. So here, of course, we have a possibility to perform this operation. This operation, let's understand what they are. And let's understand if they can be useful for our processing. So let's try to find that here. And you see here, in order to what is possible to do with this algebraic operation, let's go to the toolbox. And you see here, we have a folder that is called band algebra and if we are exploding that, you see here, we have three different possibilities. The first option is called band math, the second band ratios, and the third one is called spectral indexes. All right, in this lab, we are talking about these three possibilities that we are mentioning in this particular menu of the toolbox that we have available. And as you can realize, they are extremely interesting because they allow you to extract a lot of information with with added value. Let's start with the band math, all right? So if, as usual, when we are using that, we are going to the toolbox. In order to activate these things, we can double click on the operation, and you see, in this case, you see we have a Windows that is opened, and the title of this Windows is band math, where in this Windows, so I'm describing for the first time, then when we reuse that will not be necessary. In this first part of the menu, you see we have the previous band math expression. That means that if you have already input an expression, you can reuse this expression the second time, of course. And then we have here, you see a series of buttons. You see save, restore, clear, and delete. And here, enter an expression that the most important part of this window, in order to insert an expression, that means you can add here an operation to perform over the matrix, and I just show you how we can use this particular expression. So let's imagine to apply that to a particular band. For example, in this image on Turing acquired on the 14th of April in 2020. And let's think about to perform an operation. For example, we can reperform the operation in which we add to every single digital number a constant. So how we can, as in Excel, how we can use this expression, this formula. So I need formalism in order to perform this operation, as in Excel, of course. And in Ndbi, we have these things. And in this case, for example, the formalism of this operation is taking into account the facts to define an expression in which with a particular syntax that I try to translate for you the same operation as performed in Excel. In Ndvi, B1 plus 1000, all right? Now I try to explain what does it mean. When I write an expression, what I need, or I always done here, is to press the enter, right, after having digited the expression, because if nothing happened, that means that the syntax of this expression is correct after being pressed. If, for example, here I put the wrong operator, for example, 2 symbol plus, and I'm pressing enter, you see here, you have entered an invalid expression. Check for the syntax error or undefined procedures and function and try again. So that means that it's very important to press enter in order to check if there's any syntax error here. So I mean, this operation is very necessary and very important. In this case, of course, there's a syntax error because I put 2 different plus signs here. So if I'm deleting one of these plus sign and I repress enter, you see that I have not any message from the syntax point of view. So what B1 means in Ndvi, from this point of view, is particularly evolved because I mean, you see, in Excel, I define the formula, the expression for every single cell, and I copied this expression to every single cell for all the lines and all the columns. So you remember in Excel, for 2 columns and 3 lines. So I did need to perform and to copy the expression for the 6 different cells of the matrix that I used in Excel. Here in Ndvi, there's a very important things that you can use here. So just defining this variable that is called B1 means that B, that stands for band, and is compulsory to start and to define in Ndvi, in the expression, the variable with B. So if you have any experience in programming, you know that if you are programming, I mean, you can perform different loops. And so in this case, we can define 2 loops, one for the 2 columns and one for the 3 lines for the Excel. In this case, we have more or less 8,000 by 8,000. So I'm performing this operation for all the cells of the image. So in Ndvi, this concept of loops, that means that you are performing the same operation for all the lines and all the column, is encompassed in this variable, what we call the B1. The variable of Ndvi is a variable that has a constraint to start with the letter B. So after B, I can write whatever I want, but B encompasses a concept of cycle. So in Ndvi, B means band. So that means that the band is a matrix that is composed by different lines and different columns. So I can couple this variable to a particular band of the dataset that I have available in the data manager. So using the concept of variable and the operation of adding a constant here is performed automatically for the whole image matrix. So you can understand that in this sense, the expression that is inserted into Ndvi has a great advantage, that is defining a loop or two loops in this case to make sure that all the calculation are performed on all over the cells of the image. And so just defining this variable, this operation will be performed over the entire image. So in this case here, when we entered the image, pressing enter, you see, now this is an expression. I can click OK here, and you see, and now you see there's a very important windows in which I can couple the variable, you see variable to bands pairing. So I'm associating to the variable B1 that I wrote in the expression, and you see that is selected, and I couple that to one of the different bands. And you see that in this part of the windows, I have all the data set that are in the data manager. So you see, these are the 7 bands of that are recording reflectance coming from the ground. You see here, in brackets, we have the central wavelengths. For example, here I have the panchromatic bands at 15 meters. Here I have the cirrus, that is another bands of the mid-infrared. And here I have the thermal infrared, and I have also the quality image of the whole data set. So you see all the bands have this blue globe. That means that every single band is georeference. So let's associate it to the band B1 to the band blue, okay? Here. So now I coupled the expression, the variable, to the band 1. So that means that between here, this expression, the sum of 1000 in digital number will be added to every single cell of the blue band that is centered in 0.49 microns. Every single cell will be added to the value of 1000. So you see, as usual here, I can also define the spatial subset. So I'm modifying the original value. So that means that I can memorize these things because the values will be different. So you see here in the spatial subset, I can do on all the image or on part of the image. But in any case, we need to foresee the possibility to save the data because we are modifying. So as usual, or file or memory. And here you see the spatial subset as for example, in the pre-processing phase. So in the pre-processing phase, I have also the possibility to define the spectral subset. Of course, here I don't have this possibility because I'm coupling to the spectral subset a particular variable. So for example, here you see the pairing with a variable and the spectral. So I mean, here I don't have the spectral subset, but I have, of course, the spatial subset. So I can decide to perform the operation on full scene or part of a subset of the image. Let's leave the full scene option. And here, instead of memorizing over file, let's put that in memory. That means in the RAM memory. Let's click OK. And you see, in this case, you see I have a warning. So in this case, it's not an error Windows, but it's a warning. That is telling me that, I mean, your cache memory could not be sufficient to perform this operation because the dimension is exceeding. And so I'm warning you on this possibility. The results will be, you see here, more than 120 megabytes of the data. And the total cache size you see here is lower than that. In reality, I mean, it's warning. It is only a warning because it's paging the software. So I force that in memory, as you see here. So, and I can force the results in memory. That means in the RAM memory without writing that in a file. So that means that the image will be available since the Ndvi session is on. Right? Because when you will exit from this Ndvi session, you will lose everything if not already saved the file. All right, so let's force that in memory and press OK. And you see that now is executing the expression. So in this case, you see, it's created more in these few seconds, more than 120 megabytes of data. This is the results you see here. Of course, it's in panchromatic, in gray tones. And if I don't save it, you see here, you will have the indication in the layer manager that we have that in the first memory, in memory 1. This is the results of this operation. So if I'm right-clicking on the memory 1 here in the layer manager, and if I'm extracting the quick starts, you see here, right? So you see here, of course, I have only one single band, so I don't have the lines in the diagram because I have only one single band. And if I'm taking into consideration the histogram, you see that the histogram is moved to higher values. You see here in comparison with the original data. So I move that along the x-axis towards higher values. So I'm move that, I shift that, the histogram as in origin, I'm solidly shifting that on the image. So that means that if I'm adding a constant, and you see here, I move this histogram towards a higher value. So if I'm adding values, what does it mean? Shifting that would mean adding a constant means that I'm improving the brightness of the image. So if I'm doing the complementary operation, so if I'm subtracting a constant from all the digital number like before, that means that basically I reduce the brightness of the image. And so that means that adding or subtracting values, a constant from all the digital number, means to shift the histograms along the x-axis. That means definitely that I'm changing the brightness. If I sum a constant, I improve the brightness. If I subtracting a constant, I'm reducing the brightness. So you remember that this operation, I mean, is particularly important when you are thinking about the meaning of every single histograms, because I mean, it's relating to the improvement of the characteristics of brightness, and we will see then that we can also modify the contrast. So. You see here that I remind you that there's an auto stretch that is already set in the software. So let's close that. But this is the first time that we are creating what we can call a synthetic band. So this image is different from the original band because I mean we changed the distribution and the original values. So we don't have only calibrated the data, but we have modified these values. So that means that this is the first time that we are using and we produced what we can call synthetic bands. Synthetic because it's not a band that is acquired directly by the sensor, but is a processing of the original bands by a particular operation in this case. So you will see that the synthetic bands could be extremely important for other processing we will see later on. So you see, if you are going here again to the quick starts again, in order, and you see here, if we are reopening the quick starts of the bands, and you see if you are going to the histograms, the only one, of course, you see we can pose a problem that we can, with an algebraic operation, to improve the contrast of the image. I remind to you that in order to improve the contrast, we need, from the theoretical point of view, you remember that in the lectures, in order to improve the contrast, from the statistical point of view, we must try to increase the variance or the standard deviation of the data in order that all the data are far away from the mean value, in order to have the data more dispersed from the mean value. So from the graphical points of view, that means that if you stretch this bell and you try to enlarge this bell, that means that you are improving the variance of the data, the standard deviation of the data. So that means that these operations are called stretching, you know, from the lectures, because we are trying to improve the standard deviation. So if we are trying to enlarge this bell, starting with the assumption that is a unimodal distribution, so you see, if we can stretch that, we are widening the standard deviation, and then we are improving the contrast. So my question is how we can do these things here with a band math. So let's reopen here, double clicking the band math in the toolbox. So you see now that in the windows I have the previous expression, you see here. So I can recall the previous expression simply clicking on that. And this is not what I mean, I need in this case. So for example, I can choose another band. So for example, I can put that B2, for example, and I can try to improve the contrast. How I can improve the contrast? Of course, it's a multiplication operation, because the multiplication exactly is the possibility to improve the contrast. So the syntax is an asterisk, like in Excel. And for example, if I put asterisk 8, that means that pressing enter, that the syntax is correct. So that means that every single digital number will be multiplied by the values of 8. All right? So let's click OK here. Let's pair the variable. For example, we are taking the same bands, the blue bands, for example, we are pairing to B2 these bands. You see, B1 or B2 is the same. I put that in memory, and that will compare with, appear as to be memory 2. I force that in memory, press OK, and we are proceeding with the value, with the processing. You see here. Here is the data. You see that I have in memory too the data. All right. So if I'm checking the visibility, you see that you see that I have these values, this difference. You see that I mean something changed in the contrast, but pay attention because there's a default auto stretch that is defined over the preferences. So I mean. You see, if you are seeing here these buildings, you see, if I'm taking out these things here, you see that now we have more values, different values here. Because in this case, we improve the contrast. And improving the contrast, you see, I can take, I can see details that I cannot see before in the other image. You see here? So in this case, the value is definitely different. So if I want to, of course, to decrease the contrast of the image, instead of the multiplication, I can divide all the digital values for a constant. So this is the opposite operation that means to decrease the contrast, you know. Of course, this operation can be done also using different operators. For example, an exponential number is improving, of course, the contrast, while the square root is decreasing the contrast, of course. It's something like a division, for example. I don't want to explain all the different algebraic operation, but we want to concentrate over the results of this algebraic operation. So, you know, this is just, in this lab, we are just having some very simple examples, and then you can have more exercise by yourself using different other operators in order to have these things. All right, so for example, here you can, in the contents, for example, you can search for the syntax and all the possible operators you have available in Ndvi. And of course, I mean, you can search for everything. So what we can do, that you remember that regardless of what we are doing in this case, I mean, the image in which we have improved the contrast, the memory too, here, if I'm, for example, if I'm in the second image where I multiplied all the values, by right-clicking here, I can go to the new raster color slice. You remember, for example, here. So in this case here, you see, you remember, in these windows, I have all the different bands, and you see that I have also here. And if I'm clicking OK, you see here, I'm creating a pseudo color image in which I'm associating to every single range of digital number. For example, here from 0 to 65,000, I'm coupling to a digital number range a particular color. You remember? So this is very easy to understand. So in this case, for example, you see, I have this example. You see? All right. So in this density slicing, for example, I'm particularly interested in try to understand, and now I'm trying to zoom. I'm sorry, because, okay, I have to. So when we are using that in memory, in the RAM memory, you can have a problem, and so don't exaggerate to have all these things in RAM memory, because I mean it's very slowing down all the system. All right, so you see here, for example, in this case, all the water that is just in front of Genoa is in this Papo value, you see here, that here, when you are using this pseudo color image, you see that, for example, we use that in order to extract information from the image. You see here. So very good. So let's close the visibility of the density slicing. All right. Let's go, for example, to take into consideration what is happening in the false color image. Okay, you see here is in that position. So let's okay, let's set the priority of visualization. So I want to check the fast color. So I'm moving that top of the list. All right. So you see here, I have the false color here. So you see that in this case, the water is very dark. And that means that in the near infrared, the water is a very strong absorber of energy. So which is the digital number of the water, for example, in band 4? In this case, how can I say that? So if I'm going in display, I'm going to the cursor value here, you see, here is that symbol. You see here, I have also these icons here, that is the cursor value. So put that. You see that now in the windows, you see that I'm checking and I'm just having in these windows the values of these different values for all the sequence of image that I have in the layer manager. So you see, for example, in this case, these are the triplet of the values. So the cursor value in this particular points in the middle of the water are G and B. R is the near infrared, you see, because we have associated to the red channel the near infrared. The value is around 5,000, while in the red that is associated to the green bands and to the green that is associated to the blue bands, you see we have values higher than that. All right, in order to be sure of that, I'm going to the right button. I'm regenerated a quick starts here, you see. So this is a bigger value because what I want to perform these things as we perform with the density slicing. If I want to use the band math in order to extract all the values that are related only to water. You remember that we performed that operation using the density slicing, and now I want to use that, using the band math, and now I want to have the statistics in order to understand which is the values, the range of values in which the water is represented in this particular interval. Okay, so it's going to finish the statistics, and I want to check what is happening to our data. So we see that in the water, the near infrared, we have values around 5,000. So let's check if I can better understand which is the distribution of the digital values when I'm pointing that to water. So here it is. All right. So you see, I'm going to the I'm sorry, I'm going to the band 5, that is the near infrared. So what is called here the band right, the near infrared. So you see here, if I'm going here, you see, I have a very peak of the distribution that is centered. You see here in more or less 5,000. You see, is more or less that is the values 5 and 5, 5,500. Then I have a flex here where I have more than 6,000, and then that means that the water, this is a bimodal distribution, you see, this peak that is very high is representing all the water of the image. You see, let's move that. You see that there's a water, and you see that this peak is represented water. The second peak, this one here, that is higher, is representing what? Is representing vegetation mainly. So if I'm checking here, what is the flex points here? You see, look at the mouse, click on the with the left button of the mouse, around the 6,000 values. So this is 37,000 is the number of cells that I have with the same values. All right, so for higher value, you see here, instead of having 37 value, I have here more than 4 millions, you see. So that means that is the flex of the distribution that is representing more or less the border of water and what is not water. So that means that from 0 to 6,000, the water is there. Apart from the 0, that is definitely the border of the image. You mean the background. So I can close that, and I can think that my water in the band number 4, you see I'm moving to the water, all the water is between a very short range of digital number. So I can write an algebraic expression that allows me to extract all the values that are comprise between 4,500 and 6,000. How can I write that? So go to the enter an expression. I open the bracket, B5, you see, I take all the values that are bigger than 4,500, so major than 4,500, I close the bracket, space, and written as here, space, I open another bracket, B5 minor than 6,000, close the bracket, all right? And then what does it mean, this expression? This expression is a conditional expression that is based on the verification of two parameters that in this moment that is associated to the variable B5, that will be the near infrared. In the first condition, we will take out all the values that are bigger than 4,500, and that means that is a Boolean condition. Out of all these values bigger than 4,500, I will take all the values that are less than 6,000. So that means that I will take all the values comprised between 4,500 and 6,000. All right. So I mean, this is the syntax form of this particular expression where I want to take out to select an interval of values. I pressed enter, there are no warnings, no errors, so now I can press OK, and I can associate to the variable B5 the band number 5. All right, so you see here, I'm selecting the near infrared band. Okay, I'm associating to B5, the near infrared band B5, and I put that in memory. Well, not. Let's save that because we can have some problems. So let's use a name, a particular name, test dot, for example, and we save that, and then I click OK. Okay, the data will be overwritten, and I recalculate that. You see, that is very, very easy. You see, this is the results of this operation. So you see that in this case, you see, in a very clearly appears that all the water is very bright in white. So you see, if I'm going here with the density slice of this image, so I'm right-click here, and I perform a new raster color slice on the test dot. You see here, let's check it. You see that in this case, you see the values 0 is in purple, that is the background. So you see that I have many other values, but you see that all the values comprised between 4,500 and 6,000 are in the range of yellow, orange, and red colors. You see that in particular here I have in red and in orange all the different values. But you see also here that I have also other red cells here. So that means that in the near infrared there are other cells that appears to reflect as water, of course. You see here that could be rivers, or could be water, or could be also shadows, for example. But you see here that if I wanted with the band mat to represent the water, you see I succeed in order to perform this operation. Yeah, you see, I'm taking out the visibility of this and also the test dot here, the density slice and the other things. And you see here, I try to explain what we can perform with this operation. So we can perform another operation that is really similar to the previous one, and the results will be completely different from before. So I'm coming back to the band math, double clicking on the band math here. Okay, I'm reopening the Windows that is managing the band math operation. Okay, you see here I have all the different expression. I take in the last one. So instead of using the symbols of major and minor, you see, I'm deleting the major, I'm putting a space, and then I'm using the terms GT separated by two spaces. While the minor signs, I can put in space the things LT. What is GT and LT? GT and LT are acronyms in English. Well, GT stands from greater than, and LT stands from less than, that have the same meaning of the algebraic symbols we used before. But in this case, in this Boolean syntax, this acronym we have as the symbol equal, we have the acronym EQ. That means are similar, this operation, they are not, they are performing the same operation, but their results will be different. Because in the previous operation we performed with the algebraic symbols, what we did, we extracted all the values between 45 hundredths and 60 hundredths, and we rewrite that in the image results, in the image matrix results, with the original values. In this Boolean operation using LT and GT, if the cell, the radiometric values that is read is in that range of values, the results will be stored with the value number equal to 1. So 1 means, yes, the two conditions are respected. If the digital number read in that particular cell is out of this range of digital number, will be marked as 0 values. Let's try to do that. So press enter in order to check if it's correct. Yeah, it's correct. All right, so let's press OK, and let's associate B5 to the near infrared bands. All right, here let's choose another name. So test 1. We cannot use the same value because it's already open in the layer manager. So let's open this file here and say with this name test 1. All right, and press OK. All right, and now it's executing the operation. See here? This is the results, you see? There's nothing. So, I mean, so if the results is what I've described that before, and all the values are 0 and 1, 0, they are all the values that are not respecting the condition. 1 is all the values that are respecting the condition. This is one of the problems that comes out from the auto stretch setup that is defined in the preferences of the software. Because if I have only these values that are ranging between 0 and 1, the auto stretch, I mean, is not working in this case, especially when there are also other images in the stack of the layer manager. But pay attention that the fact that I see everything in black doesn't mean that the things here that we don't have any values, but this is only a display problem that is related to the auto stretch that is set in Ndvi self. In order to understand these things here, let's right-click that and let's use a new raster color slice. And what will happen if I'm clicking here? If it's an image that is represented in 1 and 2, I mean, we are expecting that the results of the density slicing is proposing only 2 different classes because I have only values of 0 and 1. So I mean, all the results will be split into only into two classes. Let's check if it's okay. If okay, let's associate the test one. And you see, I have only two values. You see, I was right in this case. So, for example, I want to have the water in blue as usual. I can change the values. So 0 is maroon, that is land, and in the other values I am associating the blue. All right. So you see here. Have a look at what it's happened. So in this case, you see, I've extracted all the water, you see, in a very simple way, using the band math. Whatever is blue is water, you see here, and you see there are also other cells, but apart from here, where you see, there are lakes, you see, but there are also river, you see, this is the Po River, for example. You see here that I've extracted that. You see that is very interesting, this operation, because you see that with a very simple operation using these less than and greater than LT and GT, I extracted a particular class of my image. So of course we can do millions of different algebraic operations, but now I want to pass to the second option, to the band ratios, all right? So let's try to have a look at how is working this operation. So let's double click on band ratios. Okay, all the operations that we have performed, they are based on a single bands. All right, so if I add a constant, or if I define the range with a major and minor algebraic sign, or with less than or greater than, we used only one single band. Also because we use the density slicing that is working with only one single band. While here, you see, if I have band ratios, we can also use more than one variable. So if I'm using more than one variable, I can use, for example, multiple bands in the same operation. So you see here in the band ratios, this operation is dealing with the possibility to use more bands, for example, and for example, bands ratios. So for example, if I want to use to make the ratio between the red bands and the green bands, you see here, I can execute this operation using these two bands without associating to the variables, because you see I'm not entering any expression here, because I mean in this case I mean the operation that I'm using is a ratio. So for example, so you see here enter pair, and I'm executing this operation, you see, and I can perform more band ratios in the same operation, you see. This operation is not so important, but is preliminary to what we will do with the spectral indexes. So for example, if here I'm using this algebraic operation in which for every single cell of the image in a certain position of the image matrix, we are dividing the digital number of the red band divided by the value of the same digital number of the same cell in the green value. So let's press OK. Let's put that in memory, force that in memory. All right, and let's execute this operation. All right. In this case, I mean, you see, it's not responding. You see, all right, but now you have, you see, this is the case that we have more, too much stuff in the RAM memory. So I mean, you can have the problem. So I don't have a very powerful laptop, but this is the results of the image. This is, of course, a synthetic image, of course, and you see, same problem with the RAM, you see. I mean, I have too many things in the RAM memory. So you see, I mean, the best things I can do is just to take these things here. I removing these things here, and I re-execute the operation. Double click on the band ratios. I'm reselecting the red and the green. I enter the pair. I'm pressing OK, and now I'm saving in a file. All right, called that test2.dat, for example, in this case. All right, here. All right, let's open it and let's execute pressing OK. All right. So now I'm hopefully I will have the possibility to visualize that. All right. Okay. Here it is. All right. Here is the results. So I don't have any more problems in the display of the image because it's not more in the memory, but is saved in a file. So this is, of course, a synthetic bands. You see, that is let's try to understand what is a band ratio. For example, here, let's extract from here, from this band ratio, or by right-clicking here on the layer manager, you see in the test2 files, let's extract the quick stats, all right? So let's check how they are arranging these values. And these values, you see, are a single bands, you see. So this black cross is the mean value, the two green crosses are the standard deviation, and the red crosses are maximum and minimum. And so in the y-axis, you see here all the values as comprises between 0 and 2. So let's understand what is happened. If we are performing a band ratios between the red and the green bands, that means that all the values could be a domain of existence between 0 and an infinite value. 0 when the values of the green band is bigger than the red one, infinite when the values of the green band is much bigger than the green band. For example, if the green values value is 65,000, while the same value in the green is close to 0, we will have an infinite value. And vice versa, if the values of the green band is more or less 65,000, and the red value is similar to 0, of course, the results will be 0. Usually, all these values you see are comprised between 0 and 1, more or less. So that means that when we are close to the value 1, the two values in the red and green values are similar to each other. Where they are less than 1, that means that the green values is prevailing. When the values are more than 1, it's prevailing the red band, of course. So if I'm closing here, you see here, apart from what does this image is representing, if I'm going here, for example, if I'm going to the color, I'm going to the density slice on this image, you see here that the most part of values are represented by green values. You see here. You see here, we have these values that are pointed around the values close to 1. So that means that you see, from the statistical point of view, it's very interesting the facts that if I'm taking into consideration, you see here, the peak of the distribution is from 0.8 to 0.91, in which is prevailing the green bands. If I'm going to the yellow, you see there are values that are, the most part of the values are close to 1. You see, this is very interesting from the statistical point of view, because that means that the values are, if I'm using the visible bands, I mean the values in the visible bands, in particular in this case the reflectance value recorded in the green and in the red bands are really similar to each other. You see here, this is very clear here. So I mean, their ratio is really always close to 1. So that means that these two bands are very correlated and the values are very similar, apart from particular zone here. You see here, in which you have isolated cell, in which in this case are very red. So that means that it is prevailing the value of the red band. Let's check if we have, if there are the values in which is prevailing the green bands, and you see that, I mean, there are no blue values. That means that when the values is not similar to 1, is prevailing the band red. I don't really know what is this zone, what is representing. That means should be crops. So I'm moving the visible in order to check what are represented here in the visible. So let's close it, okay? Let's put that at the top of the list. Okay, I'm moving up because I have a bunch of different values. I'm closing that, all right, and put that at top of the list. I'm sorry, this, all right. Okay, this is the near the first color. The first color, I moved the first color. You see that here, these things here, okay, let's zoom here. You see in the center, these things here. You see, if I'm closing here, these are crops that are not vegetated in this case, you see? I mean, they are not reddish, so in the first color image, so that means that it's not vegetation because it's prevailing the red reflectance. So that means that in this case that are not vegetated crops in this case, maybe that could be also very humid with humidity in it. So you see that with the band ratio, we can perform this particular operation. All right, so on the band ratio, let's perform another operation. Let's relaunch the band ratio, but we are using another operation. So in the numerator, we put the near infrared, and in the denominator, the red. I enter the pair, all right, here, and I press OK. I save the file, and I call that test 3 in this case. All right, let's open that and press OK. Okay, and we save that in a file that is called the test 3. Okay, this is the results, you see. This is the results you see here. It is completely different from before, you see. It is quite interesting because you see this is of course a synthetic image. So let's imagine which is the results. So right click and quick starts with that, all right? In order to check how these data are distributed. You see, the data are distributed between 0 and 5, more or less, with the mean value is 1 and the standard deviation is more or less 0.89. Okay, this is the histogram. You see, this histogram, there's a value that is very close to 0. I mean, this is the background, of course, that is 0. And then I have a peak here that is, let's say, it's around 0.88, all right? So that are less than 1. That means that is prevailing the reflectance in the red band, if they are less than 1. Which is this peak? I'm sorry, here. What is this peak? Again, I'm sorry. This peak will be the water, of course, because I mean, in the red is reflecting more than in the near infrared, of course. All right. You see that here I have other values that are bigger than that are more than one, in which the near infrared values is prevailing over the red. What are representing these values? These values, of course, are representing vegetation, because I mean vegetation is reflecting more in the near infrared and this has a peak of absorption in the red band. So that means that all the values that are more than one are more or less, I'm sure, that are vegetation, of course. So I mean all these values, you see, are represented in this case, and you see that in this case, all the values that are more than one, you see, when checking that, you see, in particular cases, the value of the near infrared is 5 times more than in the red, and values bigger than one are typical of vegetation. Let's check to use that to use the density slice also here. So now we want to use two different areas in which, in these two areas, you see that there's also a very dark area here, and this area will be based on the multi-temporal lab that we will have at the end of the course. And then we have a brighter area. This brighter area, you see here, are crops, of course, where the vegetation is, is on. You remember that the image was acquired in April, 14th of April. We are not in the maximum of the phenological states, but you see that, for example, here in Torino, the image is very dark because, the roof of the buildings are not reflecting very much in the near infrared. So, just recapping that. If we are performing here the density slice, okay, from here, you see we can try to perform two different classes of the different density slice. So let's clear all the color classes from here, and so we select only two classes: the first one and the second one. Okay. The second one, the first one, let's use the maroon, and the second, the blue. All right? It's better just to have the first, the blue color, and the second, the green color. All right. So the first one, we are taking the values between 0, you see here, from 1 and 0, for example. And in the second class, we are using, and you see that here, in blue, you see you have all the water, you see? We have all the river and all the water here. And in the other class, if I'm taking from 1.0001, not to use the same value, and the maximum the other, you see that all the other is appearing. So in this case, you see, using this band ratio, I can extract water and more or less all what is not water on the same image. You see here, we have all these values that you see here. That could be, you see, could be snow, for example, in April. Let's check in the near infrared. Okay, you see here is snow. That means that it's okay that is in the water class, because it's a sort of metamorphism of water. I'm sorry, I'm wrong. Okay, so you see that using this band ratio, I can use in these two classes. Let's redisplay that. Okay, I remove the other things here. All right. This is the results of the last band ratio. Okay, let's right-clicking having the new raster color slice. All right, here, press OK. All right, where I have 16 different classes by default. Let's remove all these classes, and I created only two classes. The first one in blue, that is the ranges between 0 and 1. And the second one, and you see that I have in blue, I'm sorry, here, I have all in blue all the digital number that comprises in that range, in the results of the band ratio. All right, so all the water, all the rivers, and part of lakes and snow is in that class. All right, that being the snow, a metamorphism of the water. In the second class, you see, using 1.0001, you see, as before, and here I have the maximum, you see that I have in green all the other values. Where are the series, for example? In this case, I just use 1.2. You see that in 1.2, some features are out of these two ranges. So if I'm checking what is happening, you see that here is Torino, and you see there are most part of Torino that is comprised between 1 and 1.2. So if I'm taking here 1.3, you see, I have more pieces of the urban area of Torino. 0.4, you see that all these values are comprised between 1 and 1.4. So you see that with the two color class, I defined all the vegetation and all the water, and all the green, all the blackish part, I defined what is not vegetation, and of course not water. So what is in black are urban areas or not vegetated areas, for example, in this case. So, I mean, you see that in a very simple way, I defined the different characteristics of the different surfaces that I have in my area. You see here that I have this value. All right, so I would like to finish this lab. So in order to finish with this lab, I'm talking about spectral indexes. So you see here in the toolbox, I'm going to the spectral indices, clicking twice with the left button of the mouse. And you see that for the spectral indexes, I need to select a file before of using these things here. And this is very important because in order to perform these spectral indexes, we need to use a multispectral data set in this case, because for most part of these indexes, we don't need only the visible, but also the bands in the near and in the mid infrared. So you will see that when we will use Sentinel, we will not have all the spectral indexes that are available, especially when we will use the 10 meters geometric resolution of Sentinel. So let's use the first of the top of the list. So we are using the data set with 7 different bands. All right. So we are not using. We will not use. Let's use the full extents, and we'll use the dataset with 7 bands. All right. When we have selected these things here, you see I'm enlarging these windows. You see these are all the spectral indexes. These are 36 different indexes you can use. For example, the first one is atmospherically resistant vegetation index, burnt area index. Then I have here, for example, normalized difference vegetation index, and I have also the normalized difference snow index, and so on. So you see, what are these indexes? These indexes that are fundamental for remote sensing processing, this is the possibility to extract information using these spectral indexes. So let's go to the help in this case in order to understand what these indices are. So let's go to the contents. You see, I'm having a new tab on my browser, for example, here. So you see, I'm going to the index. Of course, you should have the internet connection. And I'm searching here snow index, for example. You see, I'm clicking on snow index, and you see that there's a description of these indexes. All right. So, for example, if I'm going to the snow index, you see here, what is an index? The spectral indices are ratios in which in the numerator I have two or more bands or bands multiplied for particular weights, and in the denominator usually you have the same bands that are summed each other. So in the first part, for the normalized difference snow index, you see here NDSI is the ratio between the green minus the near infrared divided by the green plus the near infrared. That means that this index highlights snow cover using a combination of visible, typically green, and near-infrared wavelengths. Values of NDSI greater than 0.4 indicate the presence of snow. All right. So, why is happening that? The domain of validity of these values, being a normalized index, is ranging between -1 and +1, in which when this index will have a negative value, of course, when the near-infrared bands, we have digital values bigger than the green one. For example, in this case, for the vegetation, I mean, in this case, in the snow index, when you will have negative values, are vegetation, of course. When you will have positive values, that means that is prevailing the green value in comparison with the near infrared, that means that all these values will represent water and its metamorphisms. So that means, for example, the snow, because it's reflecting water and snow, especially snow, more than near infrared. So you see here that these indexes, for example, here, are representing very different things. For example, you see different features. For example, normalized difference built-up index. So if I'm subtracting from the near infrared from the mid infrared, the near infrared, I can extract the built-up area. Here I can use the normalized difference water index, for example. You see, I can extract the water in this case. If I'm going here to the Ndvi, that is very famous, you see here the normalized difference vegetation index, that is the most famous spectral index, and that is very famous. You see, it's the ratio between the difference between the near infrared and red and the near infrared plus red. Of course, in ranging between -1 and +1, and all the positive values in which there is prevailing the near infrared, of course, is vegetation. When we will have negative values, that means that will not be vegetation at all, of course. So you see, I mean, it's a very important index because with this particular index, you can extract with one very simple operation all the values that are related to vegetation, for example. You see? So In this case, you can extract whatever is vegetation and whatever is not vegetation when the values will be close to zero or negative. So all these things are very similar to band ratio, but in this case, for example, the optimized soil adjusted vegetation index, that you can see, you can adjust these things using these particular, you see particular weights, 1.5, for example, and plus 0.16. But usually are very simple. I mean, there are band ratios that can be used to extract information. So let's use these different things. So let's use the normalized vegetation index, for example, and the snow, because we are sure that they are on our images. And then for having some exercise with by yourself, use also other indexes in order to check if you can use and you can extract the water indices, the built-up index in order to check if you can extract the other feature of the image. So let's start with the normalize different vegetation index, Ndvi, and let's use that. You see, of course, you can use this index only with a data set opened with the metadata, because otherwise there are no indication of the data. And you see, this is the result. And you see that in this case, we have in the top of the list, I have the image. You see, this is the Ndvi image. This is, of course, it's another synthetic image, all right? And you see here, the water and the snow is very dark, and also the urban area and rivers are very dark. Of course, their values, they are negative values, because it's prevailing the red part in comparison, the red reflectance in comparison with the near infrared. What is bright in this image is related to vegetation, because it's reflecting more in the near infrared. All right, so if I'm going to the cursor location value, for example, in the water, you see here, in the spectral index, you see the index is minus 0.04. You see, it's negative. If I'm going to the snow here, you see, this value is quite similar to the water. You see, 0.036. If I'm going to Turin, I need to zoom and to pen in the okay, here I'm taking the cursor location value. You see here, it's just close to zero. It's plus 0.04. You see, if I'm going to a vegetation area here, you see the values is 0.25. I remind you that the index is ranging between -1 and +1. So let's create a density slice right now. So new raster color slice here. All right. Let's use place okay, and using the Ndvi. Let's clear all the classes. Let's put 3 classes, for example. The first, the second, and the third one. In the first one, we are imaging that as water in cyan, and we put that from this minimum value, that is the minus 0.23, to, for example, to minus 0.1, for example. Let's check what is happening. Okay, I'm just, I mean, trying to do that. You see that the water is not cyan. So that means that water is not here, right? You remember that was 0.04. So let's put here 0, minus 0.001, for example, all right? And you see, then now I have all the water and also the snow. You see in cyan. And also area there may be a water. You see, if I'm going to Torino, you see that the Po River is cyan. You see? See? And the city of Turin is not there. So second class could be, for example, this, I don't know, red, for example. So I can put here from let's say from minus 0.00099, all right, and here from let's say 0.1, for example, all right. And you see that in this case, you see I'm moving these windows, I'm sorry, is enlarging that, all right. And you see that in this case, I colored all the built-up area of Torino and most part of the built-up area and all this red area there that we will check in one of the last labs. And then the third class, maybe let's put that green value, that this class from 0.1001 till to the maximum, that is 6.64, you see I colored all what seems to be vegetated in this image. And you see that with using this Ndvi, I can clearly and very easily define the different classes here. All right, very good. So let's close the density slice here, right? So I'm closing here everything. So let's now performing another operation. So let's try to check if we can extract only the snow. All right. So let's not to use all the image. So let's go to the spectral indices, use the same first data set. Let's use OK. All right, enlarge the spectral indexes. Let's use the normalized difference snow index. That is, I remind you, is the ratio between the bands. Let's check it again in the snow index. Let's recap what the snow index is. All right, here, and you see that the normalized snow index is the ratio between the green and the near infrared band. All right. So let's close it. Let's use the normalized difference snow index. Let's display that on the results on our window. Let's use the whole image. Anyway, it's saving that. So I mean, we don't have any problem with the RAM memory. So in the help of the is written that all the values that are more than 0.4 are should be snow. You see that are very, very bright in this index, and together with the water, of course, that should work. You see that also the river is very bright in this case, because it's reflecting, of course, more in the green than in the near infrared. So this no cover normalized index is extracting water and its metamorphisms. Okay, let's go to the snow here. Let's use the cursor location value, and you see that in the cursor location value, in this case here, this is the spectral index 2, that is the values, that the name, the values is 0.029, that is far away from 0.4. But in this case, there are values more than 0.4. As we check in the help, you see, values of NDSI greater than 0.4 indicate the presence of snow. All right? So let's check if there are values more than 0.4. So let's have the quick stats. All right, just checking if there are values more than 0.4. So it's extracting all the values from this spectral index. The image is always, you see that the maximum value is 0.34. There are no value more than 0.4. Why that? Because I mean, this the ancillary condition. I mean, these images are acquired in April, so that means that this is the residual of the snow, and being maybe all the snow that was there
in the winter season, maybe this snow is covered also by other things, for example, impurity or pieces of leaves of vegetation, in which, I mean, this is over this snow, over the surface of the snow, there are sediments in which the reflection in the green band is lower than how is reflecting snow fresh, for example. So from the theoretical point of view, what is written in the help, I mean, should be more than 0.4, but in reality, you see, maybe it's not really like that, because we are at the end in this season of the snow precipitation in April. So, but you see that in this case is more than 0. So if that, we can right click here. So we can do that with the density slice. Or if we can also use the band math. So let's use the band math. And in this case, you see, we can enter an expression B1 space GT greater than space 0. So we are extracting all the values that are more than 0 in this case, using the Boolean operator grid GT greater than. So if for all the values there will be more than 0, the values will be 1 in the results of in the image results, and all the other values will be 0. So presenter, no error. I'm pairing B1 to the spectral index, to the last spectral index. So top of the list, that is the normalized, I'm sorry, that is the normalized differences no index. It's just here, okay, all right. Okay, I put that in, let's choose another name. So for example, test 4. And I'm taking out from the normalized snow index all the values that are more than 0, all right? So this is an image that you remember is darker. So I need here to use the density slicing. So I mean, right clicking here in the test 4, the color slice, I will have only 2 different values here, 0 and 1, you see? The first class is what is not this is not snow for sure. And the second one, for example, in white, that is snow. You see here. Okay, I'm closing these things here. I'm sorry, I need to change that. I can also change the slice from here. Okay, right click. I'm sorry. Okay, I change, if I'm not wrong from here. No, it's wrong. I don't remember, I'm sorry. Okay, anyway, you see, okay, let's redo that. So I'm sure I remove that, and I don't remember exactly the way in which we can change the color from there. Okay, we are relaunching the color slice from here. All right, the first one, 0 values, I'm associating the color maroon, and the other one, the white color. All right. Okay, you see here, and so if I'm moving that, you see that from here, I extracted all the snow in that case. Of course, also the water, but I mean, you see that all the water and all the metamorphism, all the Po River, all the hydrographic network, but also the snow and water. Okay, so with these very last things, we are finishing this 6th lab that was very intense, relatively long, but particularly important. So we will see for the lab number 7, where we are going to talk about scatter plots and digital filter. Let's see another time. Okay, take care. Bye bye.